Good morning all. In today's GATE coaching session, we are going to see a topic from Computer Organization and Architecture. I am Pushpalatha, working as an assistant professor in the Department of Computer Science and Engineering in S.A.E.C Engineering College. Let us look on to the syllabus of COA first. So this is the GATE syllabus for the subject Computer Organization and Architecture. Starts from machine instruction till I/O interface. So among these topics, I have chosen memory hierarchy. So in today's session, we will look into about what is memory hierarchy in a detailed manner. Okay, so these are the topics that we are going to see in today's session. So these topics are to be covered in today's session. First, let me give an introduction about memory hierarchy. See, this memory hierarchy is basically a structure that contains different levels of memory for data storage. So all these levels vary from one another in many features. So the important feature considered among them are the cost of the levels of memory and the size of each and every level, and also the speed to access the data from every level. So based on these speeds, the levels of memory differs from one another. Now let us see what is the purpose of this memory hierarchy. That is why we are using memory hierarchy in a computer architecture. See, this memory hierarchy is basically to make our system, that is to make our system perform well and to extract and optimize performance from the computer while accessing a data. See, data access in the sense it should be happen in a faster manner and also in an efficient manner. This data access should be done in a manner like a blink of an eye. It should not be a tedious process. So if you have stored the data in a correct manner means then the data access will also be in a simple way. So CPU is responsible for looking into the data, that is where the data gets stored and how it is being accessed. So all these operations are controlled by CPU. So this is the introduction for memory hierarchy. Now let us see why this topic is considered to be important. Okay. So memory hierarchy is considered to be important based on three features. The first one is speed, next one is size, and the last one is performance. So all these three factors, that is the speed, the size, and the performance, all these three are interrelated. Every levels of memory differ from one another based on these three features. So we are categorizing the levels and differentiating the levels of memory based on these features. First, let us say speed, size, and performance. So speed in the sense the data access should be done in a manner in a much faster way. So in various level the speed too varies according to the capacity of the memory. The next one is size. Every levels of memory differ in size also. So one memory level will not be in same size when compared to the another memory level. So depending upon the speed and size of each and every level, the performance too varies. So how it varies means if the size of the memory is in lesser ratio means then the performance will be faster. When the size increases, the performance will gets degrade. We'll see this in a detailed manner in the upcoming slides. Now let us see the levels of memory hierarchy. So these are the levels which are present in the memory hierarchy. First one is register, next is cache memory, third one is main memory, and the last one is secondary storage. Now let us see a glimpse about how these levels of memory differs from one another in an image. Okay. So consider this thing. So the register is presented at the topmost layer. That is, the register is also known as CPU register. Why? Because this register memory is placed inside the CPU. So the processor has the privilege to access the data directly from the register. CPU is responsible for making this data access. So since the register is present inside the CPU itself, so data access will happen in a faster manner. Okay, so the size of the register is considered to be small when compared to other levels of memory, but it is highly expensive. The factor cost depends on the size of the levels of memory. If the size is lesser means then the cost is going to be high. If the size is higher means then the cost is going to be cheap. So this cost depends on the size of the memory. So compared to all other levels of memory, register is considered to be extremely the fastest memory. So next to register, the next level of memory which is available is cache. One more thing is, if a level of memory is considered to be nearer to the CPU means, then the accessing time is faster. It is not like physically there is cache is present near the CPU, but it is like if the level is considered to be nearer to the CPU means, then it is considered to be then the data access is considered to be faster. In this diagram, we shall see that permanent storage is located away from CPU. That is, the level is presented at the bottom. Because of this, the data access will be much slower when considered to other levels of memory. Okay, now let's come to cache memory. See this, the data what we have accessed recently, the files or the websites what we have accessed recently will be available in this cache memory. The size of the cache is somewhat lesser when compared to other levels of memory, but the speed is extremely fast. The capacity is low, but the cost is very expensive when compared to main memory and permanent storage. So this cache is subcategorized into 3 levels, and it is named as L1 cache, L2 cache and L3 cache. The static random access memory, this component is based on this cache memory. So this cache uses this SRAM concept inside it. Okay, so the next level of memory, that is next to cache, main memory is present. Main memory is a random access memory. So this dynamic random access memory, this component is available in RAM. So when compared to cache, main memory's capacity is somewhat higher, but compared to permanent storage, main memory capacity is low. And the cost when compared to cache, main memory is considered to be little bit cheaper, but when compared to permanent storage, the cost is higher. Then compared to cache, the performance of main memory is little bit slow. When compared to permanent storage, main memory's performances, that is the speed is somewhat higher. Now at the bottom level of the memory hierarchy, we are having a permanent storage, that is nothing but a hard disk and solid state drives. So this permanent storage is used for the capacity of the permanent storage is higher when compared to all other layers. The diagram itself is represented in a triangular manner. Why? Because when compared to the previous layer, the capacity increases when we goes down. So when the capacity increases, the performance decreases while we go up. So these are the levels of memory. Now we will see in detailed manner about each level. Okay, the first thing that we are going to see in memory hierarchy, that is the first level is registers. So this registers is present inside the CPU, and it also holds data which are currently and frequently being used by the CPU. If the CPU is accessing a data then and there or more often means, that kind of data will be present inside this register. For example, data like immediate results, instructions and other needed necessary data which is required for execution of a component, all this data which is being frequently used by the CPU will be present inside the register. So the types of register are also listed down here. First one is data register, next one is address register, status register, program counter and instruction register. So these are the types of register which are available. So next we will look into the cache. So as we have already seen that the recently accessed items will be available in cache. Since the capacity of the cache is low, it gets overwrite then and there. Whenever we are accessing multiple items, the cache will be overwritten every time because the capacity is smaller. So we are accessing more number of files means the files will get overwritten every time. Okay, so let us see what is the purpose of cache memory. So the CPU takes much lesser time to access the data from cache memory. If you are making a data search, we are searching for an information in a system means the CPU will first look into the register, next it will look into the cache. Why? Because all the frequently accessed item will be available immediately inside cache. Because of this feature, the data access is considered to be very much faster. Okay, so when compared to main memory also, this cache component works in a faster way. So let us see the principle. Here two kinds of references used in this cache memory. First one is temporal locality and the second one is spatial locality. Let us see one simple example to differentiate this temporal and spatial locality. So the first one, that is this temporal locality. Say for example, if you have called your friend some 2 minutes back, okay, and you have called your mother some 5 minutes back. So the last call you have made is to your friend. The last search will be available, that is the last data item accessed will be available in this temporal locality. So recently accessed data is likely to be accessed again soon. So I have called my friend 2 minutes back and I will call my friend few minutes later also. So in that case, if the data is likely to be accessed in future also again means then it will be present in the temporal locality. Okay, I have called my friend 2 minutes back and I have called my mother 5 minutes back. So the next data which is nearer to the recently accessed item will be placed inside this spatial locality. So both of these items are somewhat related. I will call my friend and again I will make a call to my mother. So in for example, if you are going to a supermarket, means if I am getting bread, definitely I will go for milk section also. Somewhat bread and milk is related, so kind of like the temporal locality and spatial locality is also related. Okay. So next we will see what is meant by catch, miss and miss rate. So before seeing the types of catch, misses, we will see what is meant by miss rate and hit rate. Okay, I have searched for a file, let us say operating system. Recently I have looked into a document in operating system. So this is the last file I have gone through. This file will be available in the cache. Okay, if I am searching for that file again means CPU will look into the cache memory. If it is able, if the CPU is able to locate the file, identify the file in cache means then it is considered to be hit rate. That is complement of miss rate, successful access to the cache. If I am able to access the cache successfully and I am able to retrieve the data successfully, then it is called as hit rate. The next one is miss rate. So I am able to access the cache but I am not able to access the data from the cache. So this is considered to be miss rate. So now let us see what are all the types of catch misses which are available. The first one is compulsory miss. So compulsory miss is I am able to access the catch block but I am not able to access the data. So here what is done is you have accessed the catch. That is what the thing which has been done here. Such a kind of miss is called as compulsory miss. Second one is capacity miss. See, capacity miss is I am having huge number of blocks but I can't place all those blocks inside cache. I have gone through huge number of files recently. For example, 15 to 20 files recently means the cache capacity is only to store 5 files means then it can't store all those 20 files I have referred. If the capacity of the cache is to store 5 files means then it can store only 5 files. So all the recently accessed file items will be overwritten. So I can't dump all those blocks into the cache. So this is called as capacity misses. The last one is conflict misses, means multiple blocks are multiple blocks are competing with each other to occupy the cache block. So such a in that case every block can't occupy the cache space. Any one block shall make it a win and others shall make it a miss. So such a kind of miss is called as conflict misses. So this is catch, miss and hit rate. So next one is main memory, nothing but a random access memory. So this is considered to be faster when compared to a secondary storage. When compared to cache, this is considered to be a bit slow. So in RAM there are two types. One is static RAM, that is SRAM. This SRAM is used in cache also. We have already seen in the diagram also. So this SRAM is considered to be much faster and it is also considered to be expensive. If a level of memory is considered to be faster means and the capacity is definitely going to be less and the cost is definitely going to be high. In that scenario, performance is also going to be high. Okay, so the next type of RAM is dynamic RAM, which is DRAM. So when compared to other, it is considered to be slower. Since it is slower, it is also a cheaper version used for making this main memory. The two kind of memory access is also being given. So one is random access, another one is sequential access. See, random access is a thing we can access a directory, and we can what is it? If I am searching for a file means, then I can search it anywhere randomly. I can search in a random manner means then it comes under random access. Sequential access means we have to go through one by one. That is, the search is being made in an order one by one. So a very good example for this is tape storage. So if I am storing the data means then I have to store it in a order. So in that case, the search is also going to be done in an order. So such a kind of thing is called as sequential access. Okay, so the last kind of memory is there is the level of memory which is present at the bottommost is the secondary storage. The secondary storage is nothing but a permanent storage. So in secondary storage, I think all of us will be familiar. So secondary storage, the thing is hard disk. So our hard disk is considered to be a permanent storage, which is made up of magnetic storages. Compared to all other levels of memory, this is considered to be the most slower performing level. So next to hard disk drives, nowadays people are also using solid state drives are also being used in the manufacturing of computers and all. So the solid state drive is considered to be faster than HDD hard disk drive, but the cost is expensive. Okay, let us see the impact of performance of this hard disk, that is secondary storage. When compared to main memory, this secondary storage, as we have already seen, the performance is going to be slower when compared to all other levels. Why we are using secondary storage means the capacity when compared to all other levels is very huge. So we can store as much of data we want, and this secondary storage is used for storing the applications what the user works, and the user's personal and official data can also be stored in this secondary storage. Okay, now this performance metrics, how we are evaluating the performance of each and every levels of memory. So these are the features which are used to measure the performance. The first one is access time. See, the access time is nothing but the time taken to access the specific data from a memory level is called as access time. Latency is I am requesting for a data, then the data is being searched and I am getting the data. The time between the request and response is known as latency. That is a time delay. Latency is also known as time delay. Last one is bandwidth. So bandwidth is something the rate at which the data is used to the data read and write is being done. The rate is known as this bandwidth. So based on all these things, the performance of each and every level is can be evaluated. Okay, so I think I have done all the theory parts. So we have gone through all the levels of memories and the performance and how each and every levels of memory varies, which one is considered to be the most efficient. If the capacity is small and the performance high means which is performing well is considered to be the most efficient memory. But of course every level comes with its own merits and as well as its demerits. Okay, so we have done with the theory part. So based on the levels of memory what we have seen, so some problems have been listed out. We'll look into the problem. Okay, the first problem is based on catch miss. Okay, let me read out the question first. A system uses a 4-way set associative catch with 128 sets. The catch block size is 64 bytes and the total catch size is 32 KB. What is the total number of blocks in the catch? Okay, so here the data which has been given is the catch block size is mentioned as 64, whereas the total catch size is mentioned as 32 kb. We have to find the total number of blocks that are available in the catch. Okay, so these are the options which have been given, and let us use a formula to find this. So in order to find the number of blocks which are available in catch, the formula used is total blocks is equal to size of the catch divided by size of the block. Now let us see the catch size is 32 kb. Okay, I have mentioned it here, and the block size is 64 kb. It is mentioned here, so we have given those datas here. So one thing what we have to note down here is this catch size is mentioned in kilobytes and block size is mentioned in bytes. So we are converting this kb into bytes, so that is why I am multiplying this 32 with 1024. Okay, after multiplying and performing all those calculations, we'll be getting the result 512. So let us see whether it is available in the options. Yes, it is available. So the answer for this question is option C, 512 bytes. Okay, so the total number of blocks in the catch is 512. Okay, let us see the next problem. So the next problem is from direct map to catch. Again, it is from catch level of memory. Okay, let us see the question. In a direct map to catch, there are 1024 blocks in the catch. Okay, so in this catch, 1024 blocks are available. The catch block size is 64 bytes and the total address space is 32 bits. How many bits are used for the block offset in the catch? So we have to find the number of bits for the block offset. The options have been listed down there. So the block offset means it is the number of bits which is used to address a specific byte which is available within the catch block. So the catch block size is mentioned as 64 byte. So we need to determine the number of bits which are used to address these 64 bytes. Okay, let us use the formula for this. So in order to find the number of bits of the block offset, the formula here is we have to just find the log base 2 for the block size. So block size is 64. So we have to find the log to the base of 2. For 64 is 6. Whether the option is available? Yes, it is available. So the answer for this question is option A. So we will see some 10 problems here. Each and every problem is solved with the help of some simple formula. There is no other go, we have to go with this formula. So let us see the next problem. So third problem is catch, hit and miss rate. Okay, so let us see the question. In a system with a different mapped catch, the following information is provided. Okay, so there is a direct mapped catch and the following information provided are the catch hit time, which is 2 cycles, and the catch miss rate, which is 10%, and the memory access time is 100 cycles. Okay, the hit time is mentioned here and the miss rate is mentioned here. Also the time which is used to access the memory is also mentioned as 100 cycles. And what we have to find in this problem is what is the average memory access time. So we have to find the average memory access time. How long will it take to access those data? So we have to find it. So options have been listed here: 12 cycles, 20 cycles, 110 cycles, 1 or 2 cycles. So the unit here often mentioned here will be cycles and nanoseconds. So cycles is mentioned as cycles and nanosecond is mentioned as ns. We'll see the explanation for this problem. Okay, so in order to find the average memory access time, that is in short we call it as AMAT. So the formula for finding the average memory access time is hit time plus miss rate into miss penalty. First of all, we have to find whether all these data are available. Is it available? Yes, the hit time has been given, which is 2 cycles, and the miss rate is also given, that is 10%. We are converting this 10% into 0.1 by dividing this 10 by 100. So after dividing this 10 by 100, we will be getting 0.1. So next, the miss penalty. For miss penalty, here the data given is memory access time, that is 100 cycles. So I am taking that value for miss penalty. Okay, whether I am having all the data to find the average memory access time? Yes, I am having. Okay, I am substituting all those data there. hit time is 2 cycles, so 2, miss rate is 0.1, okay, and miss penalty is 100 cycles, okay. So after performing all these calculations, the final answer I am getting is 12 cycles. Whether the answer is available in the option, let us see. Yes, 12 cycles, so option A is the answer for this problem. Okay, now let us see the fourth problem. This fourth problem is based on virtual memory and paging. See, this virtual memory and paging concept is also considered to be important in CO also. So this concept will be covered in operating systems also. So virtual memory is a thing where it occupies a storage from the secondary itself, but it will be considered to be somewhere else. That is why the concept virtual is used. Let us see one problem in virtual memory also. In a system with a page size of 4 KB, the virtual address is 32 bits and the physical memory size is 1 GB. So the component what we have to look into is the size of the physical memory, that is 1 GB, and how many bits are required for the page table entry. Why this page table is being used here is, see, they will be having a physical address and the virtual address. So both these have to be matched in order to find the original location of the data. So page table entry is considered to be an important feature in virtual memory as well as paging. Okay, so these are the options which have been listed down. Now let us see the explanation for this problem. So to determine the page table entry, we need to calculate the number of bits that is needed for addressing the physical memory. Okay, so we have seen the size of the physical memory is 1 GB. The data has been given. So this 1 GB is converted into bytes. So I am converting this, I am taking this 1 GB as 2 to the power of 30. Why? Because this GB is converted into bytes. So next one is page size. Here the page size is mentioned as 4 KB. Again I am converting this KB to bytes. So page size, this 4 KB is converted into 2 to the power of 12. After solving all these equations, I will be getting the answer 2 to the power of 18. So the power 18, this is considered to be the number of bits. So the 18 is the required address for frames in the physical address. So this option is present. So 18, option B, 18 bits is the answer for this question. Okay, next the fifth problem, which is the cache access time. Let us see the question. A computer system has the following characteristics. So this is also this is a similar problem what we have seen 2 problems back for finding the average memory access time. Same formula can be used. So let us see what are the data they have given. Cache hit time is 5 nanoseconds. Main memory access time is 50 nanoseconds. Cache miss penalty is 100 nanoseconds. So if the cache hit rate is 90%, what is the average memory access time? We have to find out. So these are the options that have been listed. Let us see the explanation. Okay, same formula for finding the average memory access time, hit time plus miss rate into miss penalty. We are having all these data. So this here the miss rate, the miss rate is mentioned as 1. So we are converting this into 0.1, and the miss penalty is the access time for main memory. We are adding this 150 nanoseconds. That is main memory access time, and cache miss penalty is being added, and the value is considered here. So this is considered as the access time to main memory. So we are adding all these values into the components, and we are finally evaluating it as 20 nanosecond. Yes, option A, 20 nanosecond is the answer for this question. Okay, now let us look into the 6th question. This is based on memory hierarchy efficiency. Okay, let us see the question. A system with a multi-level memory hierarchy has 3-level cache. We have already seen in the diagram that cache is categorized into 3 levels, L1, L2 and L3. Here L1 and L2 cache hit time has been mentioned. So L1's hit time is 2 nanoseconds and L2's hit time is 12 nanoseconds. Main memory access time is also given. There is 100 ns. The miss rates for L1, L2 and main memory are 5%. 10% and 100% respectively. What is the average memory access time? So again we have to find what is the AMAT value. So here a different formula is being used. So in previous example we have used this formula, hit time plus miss rate into miss penalty. Since L1 and L2 catch values are given here a different formula is being used, L1 hit time plus L1 miss rate into L2 hit time. So we have to use this formula to find the average memory access time. So all these values have been given, the percentage is converted into the given values. Okay, so now we are substituting all these values into the parameters. Finally we are arriving at the answer 3.1 nanosecond. So what is the average memory access time for this L1 and L2 catch hit? It is 3.1 nanosecond. Okay, now let's look into the next problem. So this is based on catch block size. Let's look into the question. A computer has a catch with 4 sets and 16 blocks. So it has 4 sets and the block size is 16. If a catch block size is 64 bytes and the system uses direct mapped catching, how many bits are required to index the catch? Okay, here we have to calculate the number of index bits. So we are using the log again. So log to the base of 2, number of sets is nothing but 4. So let us see the explanation. So log to the base of 2 of 4 is 2 bits. So answer for this question is 2. So how many bits are required to index into the catch? That is 2 bits. Let us see the next problem. This is catch size calculation. Here we are calculating number of blocks. This is the second example we are seeing. First problem is also based on this problem. Let us see the question first. Given a system with 16 kilobyte catch and a block size of 32 bytes, how many blocks are there in the catch? We have to find the number of block size. So catch size and block size are needed. So 16 KB and 32 bytes. So these are the values. So catch size 16 KB is multiplied into 1024 for converting the KB to bytes. Block size is already available in bytes. So we are substituting the values and we are arriving at an answer 512 blocks. So how many blocks are there in the catch? 512 blocks are available. Okay, next problem. This is for calculating the catch miss rate. Let us see. So again average memory access time formula is also being here, but it is rearranged to find the miss rate. First let us look into the question, then we will solve this problem. So the question is, a system has a catch with a hit time of 8 nanoseconds and a miss penalty of 100 nanoseconds. So the hit time is 8 and the miss penalty is 100. If the average memory access time is 30 nanoseconds. Here the AMAT value is given, that is 30 nanoseconds. What is the catch miss rate? We have to find out here. First let us, I have given the formula for AMAT, that is hit time plus miss rate into miss penalty. But what we have to find out is miss rate. So in order to find the miss rate, we have to rearrange this formula as likewise. Miss rate is equal to AMAT minus hit time by miss penalty. So average memory access time, we are reducing it with the hit time and dividing it by miss penalty. Okay, let us see the explanation. So the average memory access time is 30 nanosecond, hit time is 8 nanosecond, miss penalty is 100 nanosecond. We are substituting all these values in those parameters and we are arriving at a value of 0.22. We have to mention it in percentage, so 22%. So what is the catch miss rate? That is 22%. So this is our final problem that is based on catch organization. In a system with a 4-way set associative catch, the number of set is 32. So we have to look into the number of sets which is given as 32. What is the number of blocks in the catch? If the catch block size is 64 bits. Here also we have to find the number of blocks. This is also one example. Okay, number of blocks is equal to number of sets into associativity. Let us see the explanation for this program. We know what is the number of sets, that is 32, and the associativity it has mentioned as 4-way in the question. The block size is 64. Okay, so these two values is enough for the calculation. Number of blocks is equal to number of sets into associativity. Number of set is 32, associativity is 4. So we are getting 128 as the answers. Okay, in this session we have covered about memory level hierarchies, both theoretical and problematic concepts. Hope this session is useful to you. We will see in the next session. So until and unless, thank you.